All right, nerds. Unit 1.7. It says A, but there is no B. It's just unit 1.7. Rational functions and end behavior. So we're talking about rational functions. We're talking about how they behave specifically at their endings, but before we get to the endings, maybe some of the stuff that's going on in the interior of the graph. You know, because the endings are like the far left and you can't see both hands. There they are. Far left and far right. Okay. What is a rational number? What does the word rational mean in mathematics? Rational means essentially fraction. Rational means fraction. A rational number is a fraction of integers. Integer on top, integer on bottom. Integers are whole numbers, positive or negative. Similarly, if you make a ratio out of polynomials, specifically when there's x's in the bottom of the fraction, then we call that a rational function. So if you have x's in the bottom of fractions, rational functions. There they go. Now, rational functions will often have restricted domains. But why? Because the bottom of the fraction could be a polynomial. It could be a thing, like what we studied in units 1.4 through 1.6, that has zeros, which means a polynomial on the bottom of your fraction could have the ability to equal 0. But the bottom of a fraction is never allowed to equal 0. You can never divide by 0. So we will be on the hunt for places that make the bottom of our fractions equal 0. Those are domain restrictions. They're gaps in the domain of our function. If we call n of x the numerator and d of x the denominator, and both n of x and d of x are polynomials, meaning, you know, x's with whole positive exponents, as long as the bottom of the fraction, denominator of x, does not equal 0, then that rational function can be said to be r of x, where r of x just stands for rational, is the numerator polynomial over the denominator polynomial, keeping in mind that the denominator polynomial will never be allowed to equal 0. This is a capital D denominator. You did that in algebra 2. Here's a rational function. And our instructions are to find its domain. Now, we don't need to know the graph of this thing. All we need to do is figure out what would have caused problems. And the only thing that you know of that causes problems when you're talking fractions is when the bottom equals 0. The bottom is a quadratic. How many times can a quadratic equal 0? Twice. It's degree 2. Meaning this quadratic could have 2 zeros, meaning there could be 2 different x's that make the bottom of this fraction equal 0. Never divide by 0. So what are we going to do? We're going to figure out what makes that quadratic equal 0. Yes? What did you write on the bubble above it? R of x equals n of x over d of x. X squared minus 8x plus 12. I know you're used to writing things equal 0, but this is the bottom of the fraction. The bottom fraction can't be 0, so we say can't equal 0, just like that. And we're going to solve for x, but instead of saying what x equals, we're saying specifically what x is never allowed to equal. There's several ways of solving for a quadratic. One of them, if you hate yourself, is the quadratic formula. The other one is the one that is the preferred method, is factoring, and yes, is factors. There are 2 numbers that multiply to positive 12 that add to negative 8. Those 2 numbers are negative 2 and negative 6. This gives us 2 numbers that x could never equal. It's always what makes the inside be 0. You know, we specifically are trying to avoid 0, right? So x cannot be 2. X cannot be 6. But it could be any other number known to man or not known. Any other number other than 2 and 6. So how do we describe everything except for 2 and 6? Well, we would say first we're talking about all the numbers to the left of 2. And then also all the numbers from 2 to 6. And then lastly, all the numbers to the right of 6. There you have it. That is the domain of our function. This is showing us our domain restrictions. This is showing us what the domain is, the x's you are allowed to use. Everything except for 2 and 6. Cool with that idea? We Gucci here? Yeah? Okay. In the last lesson, I think it was the last one, 1.6. It might have been 1.5, I'm not sure now, but it was the one where we talked about in behavior of polynomials. We used limit notation. We're also going to use arrows within our limit notation, so we've got a thing here all about arrow notation, I guess you could call it. Throughout this course, we will use arrow notation to show that x or f of x is approaching a particular value, or a not value like an infinity. This table below is going to summarize some of those things. All of it should look really familiar to you, except for maybe these first two. These first two are probably the only two that look different. I mean, this says x goes to positive infinity. That means x increases without bound. This says x goes to negative infinity. That means x decreases without bound. F of x goes to a number. That just means your y values are approaching a value. F of x goes to infinity. Your y values outputs are increasing without bound. F of x goes to negative infinity. Your y values outputs are decreasing without bound. You should have seen all of that in Algebra 2. Now, what you probably didn't see was this. This says as x approaches a from the left, and this says as x approaches a from the right. And the reason why we use that superscript of minus or plus is because if you would like to be to the left of a number on the number line, you'd have to subtract something from it, wouldn't you? And if you wanted to be to the right of a number on the number line, you'd have to add something to it. And when we say something, we're talking about something remarkably small. So let's say I was approaching x equals 2 from the left. Then I could say, oh, x is like 1.99999999999. You see, that's just a little bit to the left of x equals 2. And if I was approaching x equals 2 from the right, then I could use a number like 2.00000000001. See, it's just a hair to the right of 2. Okay? So we're getting close to a number a. That's what that says. Close, but a little bit less. Close, but a little bit more. From the left, from the right. Cool? The rest of these symbols all look familiar? Yes, yes, fantastic. Yes, okay, great. Rational functions have what we call asymptotes. On this page, we will specifically talk about vertical asymptotes as well as horizontal asymptotes. Do all rational functions have vertical asymptotes? No. Do all rational functions have horizontal asymptotes? No. But they are structures that we see often in our rational functions. All vertical asymptotes are, ready for this? Vertical lines. They're all vertical lines, okay? And all vertical lines have the same kind of equation. They are all x equals some number. We will say that number is a, meaning it could be any number we want it to be. When your graph gets close to a number that is a domain restriction, you're always going to see a similar kind of behavior. When a graph gets close to a domain restriction, it either shoots up to positive infinity or down to negative infinity. And that doesn't matter if it's on the left of that domain restriction or the right of that domain restriction. Either way, you approach one of the two infinities on both sides. So does that mean I would be going to positive infinity on both sides? Well, sometimes. What about negative infinity on both sides? Well, sometimes. What about one up, one down? Sometimes. Okay, it just means whenever you get close to an asymptote, a vertical asymptote, your graph skyrockets either up or down. Always. Let's look at this graph in particular. It has an x value that it's approaching but never actually getting to. That x value is -3. This is a vertical asymptote. So let's describe our graph's asymptotic behavior around x equals -3 using limit notation. The limit as x approaches -3, but let's say we're on the left side of -3. So now I'm like right here-ish. What are my y values doing here? Are they going up or down? Up. You know what's up? Positive infinity. See, it's right here. It's headed up. Now on the right side of -3, so -3 with this little plus as a superscript, your y values are shooting downwards. Like that. So this is an example of a rational function where we have one up, one down around our vertical asymptote. Now, just like all vertical lines have a similar style of equation, all horizontal asymptotes have a similar style of equation. All vertical lines are x equals a number. All horizontal lines are y equals a number. We can't say A, so let's just say B. We can't say A because we already used A. So what is the definition of a horizontal asymptote? A horizontal asymptote is a place where the graph's behavior will approach our horizontal line. As x is doing what? As x is decreasing forever without bound or increasing forever without bound. It's essentially an end behavior. It's an end behavior because it's describing what the y values will be approaching as x gets away from 0. So as x skyrockets down or skyrockets up, our y values are heading towards this number. So essentially, a horizontal asymptote is an end behavior. For this one, let's put a horizontal line on here that this graph is getting really close to but not touching. It's at y equals 2. So for this graph, the limit as x approaches -infinity, that means as I go really far that way, what are my y values doing? It looks to me like they're getting really close to this number. They're getting really close to y equals 2. And what's going on to those y's as x goes to positive phase? So as I go really far that way, my y values are getting, oh, yeah, they're getting close to this horizontal line again. They're getting close to 2 again. Is it always true is a good question. Will they always match? When a rational function has a horizontal asymptote, the graph will always approach the horizontal asymptote for both end behaviors. I can't think of a rational function that's made up of only polynomials, top and bottom, that would break that rule. Are there ways that you can get really creative with it? Yes, but not with polynomials. If it's, x is on top and bottom with whole positive exponents, then this will always happen when there's a horizontal asymptote. Because there's not always a horizontal asymptote. But when there is, that'll always happen. Which actually leads me to what the true definition of an asymptote is. You see, some students think an asymptote is a line you can't cross. That's not true. It is possible to cross a horizontal asymptote. The graph does not need to have the same behavior on both sides. Meaning, it could cross it on one side and not the other, but it will still approach that number on both sides. But it could actually cross it on one side. And I have a picture here just to show you. It's possible for a graph to go through a horizontal asymptote, but then get close to it again, forever. Because that's what the definition of an asymptote is. The definition of an asymptote is I don't want to say line, let's just say a structure, often a line, vertical, horizontal, but not always a line. Sometimes it's a curve, but often a line that your graph will approach for all infinity. So here, even though I went through it, I will then approach it for all infinity out to this side. Now, the other direction could have looked like this. It didn't have to go through it. But either way, it's going to approach this y value for all infinity. Which then begs the question, could you cross over a vertical asymptote? No, you can't. And the reason why is because vertical asymptotes are domain restrictions. They're places where the graph doesn't exist. Vertical asymptotes will always be places where the graph doesn't exist. They are domain restrictions. And when you're talking rational functions, they will always be a place where you're trying to divide by 0. There was a hand up and now it's gone. Max, were you going to ask, could you cross a vertical asymptote? No, you weren't. So what was your question, sir? Can you cross one multiple times? You mean on one side? I don't think I've ever seen one. You can't do it with polynomials. So if your rational function is made up of polynomials on the top and bottom, then no, you can't cross it more than once. Is there ways of doing it? I mean, there are graphs that do this, and they'll look like this. So yeah, there's ways of making that happen, but not with polynomials. It takes trigonometry to pull that off, and you don't have to worry about that. It's way outside the realm of our course. Meaning, trigonometry in a rational function. That's outside the realm of our course, okay? Remember a little bit ago when I told you that not all rational functions have horizontal asymptotes? Okay. Let's talk about how we determine if a rational function has a horizontal asymptote. Now I'm going to show you 3 rules. And your job is to know these rules. You can either memorize them, which I don't suggest because, well, that's hard to do. Or you could understand why they're true. And once you understand why they're true, you'll accidentally memorize them. I suggest that, but to each their own, okay? There are 3 cases. Case number 1, the degree of your numerator, that's the top of the fraction, is less than the degree of the denominator. That means the degree on the bottom is bigger. Some math teachers will call that a bottom-heavy function. A fat bottom girl, okay? A bottom-heavy function. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is always the horizontal asymptote. The line y equals 0 is the x-axis, in case you didn't know. Let's get you an example of that. I don't know. F of x equals 3x minus 1 over x squared plus 2x minus 4? I don't know. I'm just making some crap up, okay? The point is, if you look at the degree of the top of the function, it's a degree 1 polynomial. And if you look at the degree of the bottom of the function, it's a degree 2 polynomial. This graph, if I were to graph it right now, has a horizontal asymptote that is the x-axis. Now you could just try to memorize that, or you could understand why it must be true. So let's talk about why it must be true. Horizontal asymptotes are end behavior. They're describing what happens when x is outrageous. Doesn't tell you anything about when x is small. Tells you about when x is outrageously big or outrageously small. Okay, when I say small, I mean close to 0. When I say outrageous, I mean approaching an infinity. There we go. I need to be careful what I say here. Okay. How about we say outrageous in magnitude? There we go. Because negative infinity has a very large magnitude. Imagine you take an x value. That's huge. I don't know, 10 quadrillion. That's a big number, right? And you try to plug it in. The top is going to be about 30 quadrillion. Nobody cares about -1 when you're a 30 quadrillionaire, right? The bottom goes, pleb, multiplication, exponents, baby. 10 quadrillion squared. I don't even know what that number is, but I know it's got like 26 zeros or something ridiculous like that. When you start having exponents, numbers grow really, 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 really fast. So fast that the distance between the values starts to approach infinity. Essentially, what you're dealing with at that point is something small divided by something outrageously large. Sage, we're gonna have a little mind experiment for a second here, okay? We're gonna think of a small amount of money. How about $1? Now, there's like, what, 8 billion people on our planet now? Something like that? Okay. Sage, imagine I told you we're going to take a single dollar bill and we're going to make sure that everybody in the world shares it equally. So we're going to take this $1 bill and we're going to divide it amongst the 8 billion individuals. Sage, how much do you think you would actually end up with?
1/8 billionth of it?
1/8 billionth. And what would that look like as a decimal? How many zeros would there be? A lot?
8.
A lot. It's not 8. But it's actually more than 8. But what is that essentially equal to?
Nothing.
Oh, how about that? Nothing. You see, that's why this rule works. Essentially what it does is it lets the top be a small number, a small value, and the bottom will scream towards an infinity. So anytime you've got a small over an infinity of, I don't care if it's positive infinity or negative infinity, it doesn't matter. Anytime you've got a small over an infinity, you're going to 0. Yes?
What if x was like 1?
But I said when x is gigantic. Doesn't tell you anything about when x is small in magnitude around x equals 0. It only tells you what's going on when x is outrageous. So that's why we call it an end, because it's like the ends, the far left to far right. Doesn't tell you about the center. Okay? So you could try to memorize it, or you could know why it has to be true. And if you know why it has to be true, you will accidentally memorize it. But what if the degrees are equal? What if the degrees are equal? The degree of the numerator equals the degree of the denominator. Then what we say is the ratio, fraction, the ratio of the leading coefficients is actually going to be the horizontal asymptote. You're going to end up with y equals some other number, some a divided by b. Not to be mistaken with this a and b that I have up here. It just means some number. It'll be a fraction that's not 0. For example, I'm just making some stuff up here, okay? The degree of the numerator is 4. The degree of the denominator is 4. I'm aware that I wrote the numerator out of order. I did that on purpose. Because it's your job to always be looking for the degree, knowing that it's the biggest exponent. Our horizontal asymptote, which I will allow you to abbreviate as HA in your work. Don't do that on the test, please. I still have people writing AROC on their tests. You will not receive credit for that on the AP exam. AROC is a shortcut that I write. It's average rate of change, okay? Please start using the actual words on the tests. Our horizontal asymptote is y equals the leading coefficient of the numerator, -3, over the leading coefficient of the denominator, 5. So as x gets outrageously large in magnitude, meaning heads towards positive infinity or towards negative infinity, either one, this thing's y values would get closer and closer and closer to that. Could they ever actually equal that number? Yes, they could, because you're allowed to cross over horizontal asymptotes. The point is that it would probably happen somewhere close to x equals 0. Close to it, not dead on it, but close to it. But what's happening at the far infinities, that's what we're discussing here. At the far infinities, our graph will get close to this horizontal line. So we have a horizontal line when the degree of the numerator is smaller than the degree of the denominator. We have a horizontal line when the degree of the numerator is equal to the degree of the denominator. But what if it's top heavy? What if the degree of the numerator is bigger than the degree of the denominator? The graph will have no horizontal asymptote. It'll have something else. But it won't be a horizontal line as an asymptote. Here's an example. How about we take this one that I started with and I flip it upside down? This has no horizontal asymptote because the degree of the numerator is bigger than the degree of the denominator. See, we stop using the terminology horizontal asymptote the higher we climb in mathematics because it's a specific kind of end behavior. When we could just use terminology that describes all of the end behaviors. We stop saying horizontal asymptote and we start saying end behavior asymptote. Horizontal asymptotes, they are a specific kind of end behavior asymptote. They're a horizontal end behavior asymptote. But end behavior asymptotes don't have to be horizontal. They could be horizontal, they could be slanted, they could be quadratic, they could be cubic, they could be whatever we want them to be. We'll talk about that a little bit more on the next page. This one does not have a horizontal asymptote, but it does have an end behavior asymptote. Now, I'm not sure if that's part of our curriculum or not. We'll find out next week. Let's find our horizontal asymptotes, if they exist, and then give a reason as to why they exist. Lots of people instantly got this wrong last period. Class, what is the degree of the numerator?
1. 0.
So we're hearing a lot of zeros and a lot of ones. One of them is correct. Is there an x on top?
No.
There could be, though. And if I put it there, what would the exponent be on it so that I didn't have to write it? A 0. Because what is x to the 0? 1. I could think of this as saying 1x to the 0. This is a degree 0 polynomial.
Well, what if there's just not an x there? It's just 1.
There is no x there. See? That makes it degree 0.
Oh, alright.
Because what's the degree of that? X right there. What's its degree? That's a degree 1. What's that one's degree? 2. This is a degree 2 polynomial. It's a degree 0 because there is not an x up there.
This might be a dumb question.
It might be a dumb question, but it might not be a dumb question. Let's hear it.
Does 1 have a degree of 0 or a degree of 1?
I just told you that. Look.
So you said x has a degree of
No, x to the 0 is a degree 0. What does x to the 0 equal?
1.
1. There you go. It answers your question.
But what is 1 to the 0 equal?
1 is... No, everything to the 0 is 1 except for 0 to the 0. But every real number is a degree 0 polynomial. 2 is a degree 0 polynomial. 3 is a degree 0 polynomial because there's no x's. Okay? Yep.
If you see just like someone written 1, could you like would you assume it was 1 to the 1 or 1 to the 0?
If you write a number, that number is always to the first power.
Exactly. That's what I was asking.
No, but that's not the degree of the number, though. All numbers are degree 0. That's not what he asked, though. You asked what the degree of a number is. The degree of all numbers is 0. All numbers are degree 0. But when you write them, the assumption is they have an exponent of 1. But they're still degree 0 because there's no x.
So you're saying that any time ever in the history of math that I see the number 1, I could technically write it as x to the 0? What? That's a good question.
1 is the number 1. Anything raised to the 0 power other than 0 equals 1. Please don't go around replacing 1s with x to the 0s.
But I technically could.
And you technically could do a lot of things that you shouldn't do. Like you could technically stab Cooper right now. That doesn't mean you should. Okay? Okay. All right. Anyway, dang it. I wrote degree 0 on the bottom. He got me way off topic. It's degree 2. Anyway. How do we know we have a horizontal asymptote? Well, we know we have a horizontal asymptote because it's not a top-heavy function. What kind of horizontal asymptote do we have? Y equals 0 is the horizontal asymptote. Why is y equals 0 the horizontal asymptote? Because the degree of the numerator is less than the degree of the denominator. How do you spell this freaking word? Nator. There we go. Stupid. Did you know that Einstein had trouble remembering which was the numerator, which was the denominator? True fact. He was regularly seen walking into university lecture halls, like, lecture hall, got like a couple hundred people in it, sitting there waiting for a lecture to start. Einstein would walk in, walk up to the podium, take a little piece of paper out of the podium, read it, put it back, and then leave. And what he was doing was, he was looking at this. Because he was about to go talk with other mathematicians and he didn't want to look dumb. No joke. True story. Hilarious. Anyway, next. What I see here is degree 1 on the top and bottom. Degree 1 on the top and bottom. So since they're the same degree, I know there's a horizontal asymptote. Specifically, leading coefficient of the numerator divided by leading coefficient of the denominator, because there is a 1 here in front of this x, we just don't have to write it. So y equals 3 is our horizontal asymptote, and we can just say because the degree of the numerator equals the degree of the denominator. Okay. Lastly, top heavy. No horizontal asymptote. Because degree of numerator is larger than degree of denominator. And when you are writing your verbal explanations of stuff on the AP exam, please don't use symbols like I did for equals and greater than. Please use the words. We need to be using words. I'm only doing that for note-taking purposes to make our lives easier, okay? Just like you won't write HA, because it looks like, ha! No, it's horizontal asymptote, okay? So what if something is actually top-heavy? What if the degree of the numerator is larger than the degree of the denominator? What determines its behavior? Well, I'm so glad you asked. The end behavior of a rational function will be affected most by the polynomial with the greater degree. That's why we care about bottom heavy and top heavy. And this, as its input values will dominate the values of the rational function for input values of large magnitude. What that means is the bigger degree gets to boss the y values around. It dominates them. For input values of large magnitude, that means towards positive or negative infinity, a polynomial is dominated by its leading term. So this thing on top looks more and more and more like a 2x to the fifth as x gets ridiculous. This thing on the bottom looks more and more and more like an x to the third without the plus 2 as x gets bigger and bigger and bigger. What that means is we could say as x grows in magnitude without bound, so that means to positive infinity or negative infinity, the graph of this thing starts to look more and more and more like that, because its y values begin to be dominated by the leading term. So let's just say as x goes towards positive or negative infinity, f of x will be approximately calculated by 2x to the fifth divided by x to the third. Imagine you were a quadrillionaire and then you cubed your money. Would you really, really care if someone said, hey, here's an extra $2, bub? No. You're already rich enough to buy the solar system. You don't care about another $2. Okay? So as x gets huge, screw it. And as x gets big enough, screw that too. And it starts to do that. Oh, and by the way, that reduces. It reduces to 2x squared. And because of our last unit, everybody in the room should be comfortable knowing what the ends of this graph look like. What do the ends of this graph look like? Both up. Yep. They look like this. So guess what this does as x grows in magnitude without bound? It does this. So this thing's end behavior is this. So I could say the limit as x approaches either positive or negative infinity. Nobody cares which one since they're the same. Actually, you know what? I'll write them separate. The limit as x approaches negative infinity, so let's go left, of f of x is up. And the limit as x approaches positive infinity for f of x, that's this side, also up. Now someone last period asked, could I show them what that kind of looks like on Monday? And I said I could do it right now, so I've got it on Desmos. Now, unfortunately, it won't be on camera, so I'm just going to pause the video. Okay, so last question, now that I showed you Desmos, this one. Your leading term of the numerator is this one, because it has the biggest degree. This is the leading term of the denominator. So we say, as x approaches either of the infinities, our function will start to look like negative 5x to the fourth over x. And that reduces. So our function will start to look like negative 5x to the third. And I'm hoping, because we just tested on it, that you all know that a negative cubic has endings that go left up, right down. So that tells you what the end behavior for our f of x looks like. The limit as x goes to negative infinity of your function is left up, and the limit as x goes to positive infinity of your function is right down. We made it, nerds.